The second big idea of AP Computer Science principles is data. This topic is going to be about 17 to 22% of the multiple choice exam. This unit focuses on how knowledge and information can be generated from binary data. In other words, how we can take electrons stored in physical computers and turn that into things we know, into pictures and characters and words. There's a lot of vocab to unpack in a couple techniques, so let's jump right into it. The first thing we need to do is clarify what we mean by data. In computer science, data is most likely going to be represented by a bit, which is a shorthand for a binary digit. A binary digit is just a value that's either going to be, in most cases, we'll say 0 or 1, or you could think of it like on or off, because it's probably going to represent the presence of a certain amount of voltage in an actual circuit. We don't normally use one bit at a time. We're going to use collections of bits, the first grouping of which is called a byte, which is at 8 bits. And beyond that, we have things like kilobytes, megabytes, gigabytes, and terabytes, which you should know as a shorthand just for practical purposes for using computers. The other important concept we need to know to understand data is called abstraction. Abstraction is where we reduce the complexity and small details of something in order to just focus in on the main ideas. So for example, with bits, we could take a group of bits and have it represent something like the letter A, the color red, or maybe a specific sound. When we communicate that to other people, we don't need to tell them the ones and zeros specifically that go into the letter A. We can just tell them that it's a group of bits representing the letter A and not worry about those small details. That way we can focus on the big picture and get a lot more things done more efficiently. The way we can tell the difference between whether a group of bits should be an A or a red or a sound or some other sort of feedback is going to be given by context. Opening a set of bits in a word processor versus opening it up in a music player are going to lead to different results. And so that context is important to know what those bits eventually represent. We have to be able to take all data and turn it into bits if we want to store it onto a computer. But the problem is in the real world, most data is going to be continuous, also known as analog data. The sound of my voice is a continuous stream of vibrations in air molecules. So to turn that into something digital, we use a process called sampling, where it's set intervals of time, usually on the scale of hundreds, if not tens of thousands of seconds. We take samples of that continuous waveform to turn it into something digital, to turn it into something that at its heart can be represented via binary. Because of this, there are limitations to what type of data and how much data can be stored on a computing device. Sometimes those limitations are built into the programming language. For a number, they'll only allow so many bits to store the value. Or it could be a physical limitation. It might be able to hold as many bits as possible, but that possibility is going to be limited by the hard drive or the memory on the computer. This, in turn, will limit the potential outputs of my program. If I have a calculator that can't go higher than 8 digits, it won't be able to tell me anything that is 9 digits or above that. There are some ways around this where computers will make approximations, but if we're dealing with a high level of precision, this could cause problems. If you have a calculator for money, and the final answer is always 1 cent off, it might not seem like a big deal, but if you're making tens of thousands, if not millions, of calculations every day, or every hour, those little mistakes will add up. And so you have to be clear ahead of time what approximations are being made and what might get lost every time something is converted into a digital form. Being able to read binary is going to be very important for the exam, and to understand how we can take ones and zeros and represent a huge variety of values. The simplest way to interpret binary would be to turn it into our decimal value. Decimal is just a base 10 number like we usually use on our day-to-day life. And we use a system called positional notation to figure that out. What positional notation tells us is that we take our number base. In binary, it's 2, and decimal we're used to is 10. And we use the position, that's the name, of the number to tell us what power to raise that number base to. So for example, in binary, the rightmost digit will be 2 raised to the power of 0 times whatever number is represented there, either the 0 or the 1. The next spot would be 2 to the power of 1 as we move leftward, then 2 to the 2, 2 to the 3, etc., etc. In base 10, we do the same thing. but with 10 to the power of 0 and then 10 to the power of 1. You sum up those results, and that tells you what the decimal representation would be in this case for that value. There are a bunch of other number bases that exist. Another one you might see is hexadecimal, where we have the characters 0 through F representing values 1 through 16. But we're not going to cover that because that's not on the AP exam. Important to know, though, especially if you deal with color. Once we have our data stored as ones and zeros, we need to compress it. If we literally represented everything with all the ones and zeros it takes, some files would be huge, way beyond the scope of what could be transferred efficiently. So we can compress data down based on things like repetition in the patterns of ones and zeros. Instead of going 1 0 1 0 1 0 1 0 1 0, we could just say 1 0 5 times. That saves us a lot of space and still conveys the same information. And there are other strategies we can use to compress it as well. Maybe using some sort of key so that different values of ones and zeros represent larger chunks of text or color or sound than what they would normally in other contexts. Because of this, you have to understand that the number of bits, the size of a file, how many megabytes, kilobytes, gigabytes, whatever something is, doesn't directly correlate to how much information it might actually convey, because that size is going to be influenced by the compression strategy. There are two ways to compress data. There are lossy strategies and lossless strategies, and those names mean exactly what they sound like. Lossy compression algorithms can reduce data a ton. They can really squeeze down large files into something very tiny and something very easily transferable. But they do it at a cost. It is, as the name implies, lossy. You lose some of the original through this process, and when you rebuild the actual file from this compressed data, it's not going to be exactly what went into that compression algorithm. In most cases, this is done in a situation where that's okay. Maybe you have a video file, and the resolution is higher than any monitor you expect it to be displayed on. You can lose some of that detail, since the end user won't be able to see that detail there anyway. Or maybe a sound file has pitches higher or lower than a person can normally hear, or that a speaker could even produce. If you want to maintain the perfect original of the file, though, you'll have to use lossless compression. This will maintain the original file in some way when you decompress it, but it is probably going to be larger than if you used a lossy strategy. At the end of the day, though, this is all going to depend on context. What is your end goal, and especially what is the end use of these files? If you're storing something that needs to be perfectly accessed later, you need to use something lossless. But if it's in a situation where the data is going to be represented in a way where the full file, where the full details won't be seen anyway, a lossy strategy is probably going to be the way to go. Now that we know how computers store this information, we need to figure out what we can do with all of it. So when I say information is a step beyond data. Data is just the raw ones and zeros, these pieces of a puzzle. And information is what we get when we start to put things together. We find patterns, we find facts, and reach conclusions from a collection of data we have. If you've taken statistics, you probably know that correlation in this case will not imply causation. Just because our data shows some pattern doesn't mean that, this is causing something to happen. But it is something that kind of implies that it's something worth looking into. Maybe there is a connection between these two factors if these two factors are related in our data. When you're doing this, though, it's important to make sure that you're drawing data from a variety of sources. There could be bias or mistakes if you use a single data set, and by using multiple data sets and aggregating those together, you can help minimize the impact of any bias or mistakes that might be present in one source alone. When you're looking at data, you have to understand that a lot of data, most data, is going to come packaged with something called metadata. The prefix meta means that this is data about data. It's information about the data you are looking at, things like file size, things like the author of the data, maybe the date it was published. When you're looking at a photo, there might be metadata on the camera that was used to take it, or even the location at which the photo was taken. This metadata is extremely useful when you're organizing these large sets of data and putting them together. But you can change this metadata and edit it without editing the actual file. For example, you could wipe the metadata off of a photo, and the photo would still look exactly the same. But it might lose some utility because you won't be able to tell where it was taken. You might not know the author and who to give credit to if you use it. When you have data sets and you want to aggregate them together or use them to reach some sort of conclusion, you're going to need to clean it up. Data, because it is made by humans, is inevitably going to be either incomplete or unorganized, which will get in the way of drawing accurate conclusions from it. Especially if you're using multiple sources, the data might not be arranged uniformly. The way I collect data and put it in a spreadsheet might be different than how one of my colleagues does it, so we can't just blindly put those two spreadsheets together. In addition, if I collect my data using something like an open field, I might have people type in their full names, I might have people put abbreviations, nicknames, mismatched capitalization, or other mistakes like that, but the data won't be uniform, and thus I can't apply uniform methods to examine it. So I need to come up with ways to clean that data that won't change its intrinsic meaning. Maybe I get rid of all the capitalization in a bunch of names just to make sure everything looks similar. This can cause an issue when we have super large data sets. On a small scale, if there's only tens or even hundreds of entries, this can be something quick. But as we scale up to millions and millions of entries, this process of cleaning the data will take processing time. And it's going to take storage. It's going to need a place to live, memory, for all this information to exist. And so this is something that's going to increase as we move forward. Now that we have this data, we need to do something with it, and computers can help us do that via processing. The programs can be used to process the data, maybe by calculating it, maybe converting the units, maybe multiplying it through by some constant to make sure they all look uniform. It can also create visualizations. These programs can go through large data sets, search through them, filter things out, and let you line things up to find patterns and correlations that might exist within the set that you wouldn't have noticed otherwise. For example, on a spreadsheet, you can rearrange and order columns so that you can see the correlation between two factors right next to each other. This is a very human side to data. We are using the computer to organize it so that we as people can draw insights from it and gain knowledge from that data. Visualizations and interactives, so graphs, infographics, and things like that, can really make patterns and trends stand out and really help motivate next steps in research. In addition, combining and clustering data from multiple sources, as I mentioned before, will help reduce this bias and can give you more solid insights and results as you have data from a variety of sources.